Now let's look at 6.2. This is what's called inconsistent systems and dependent equations. So it's basically where you get the same plane, two equations represent the same plane, or you have the intersections like a line, or you have two planes that are parallel. So try to look some of that up online as well and see, kind of get a good picture of what's going on. But first, we'll see what the algebra looks like, and then see how to do this solution. So let's take a look at this one. First thing you want to do is put this in matrix form. So it's 1, -3, 17, 1, 1, -1, 7, 2, 2, -5, 29, 5. Put in the dots, so it's your augmented matrix, like that. And again, our goal is to write the lower left-hand corner as zeros, with doing those operations, of course. So we can see kind of right away, row 1 and row 2, if you just subtract them, you're going to get a 0. So let's recopy row 1, like that. Put in our brackets. And let's do about row 1 plus negative row 2. And I like to think in terms of negatives and then adding. Not so much subtracting, because that kind of gets you messed up a little bit sometimes. And then we can continue and look at rows 2 and 3 here and here, because you must use each row. So if we do -2 row 2 plus row 3, that'll put a 0. So let's do it in 2 steps. So -2, or 1 matrix, I guess. -2 row 2 plus row 3. So we add these up, and when you do this, you get 0, -2, 10, -1, 0, -3, 15, and 1. Probably a good idea to pause the video and check that out on your own. Then we continue. Our next goal is to do what? Is to put a 0 here. So now you're looking at all of these, but you really could only use row 2 and 3. Otherwise, this 1 will put something back. So let's recopy. 1, -3, 17, 1. 0, -2, 10, and -1. Okay, so then if we do 3 row 2 plus -2 row 3, you're multiplying by one's an opposite and then by the same thing. So you end up getting 6 and -6, right? So when you do that, that product, look what happens. You get, so when you do that, you get, so you're looking, just keep in mind, you're looking up here to do that operation. Those are guaranteed to be 0. This is guaranteed to be 0, because that's why you're multiplying. Then you just got to look here and here to see what it ends up being. So you get 0, 0, and this becomes 0 as well, and then -5. Okay, so check that out. See if that makes sense to you. Then when you add, well, no, I'm sorry, not when you add. Now look at what you have. You actually have 0 times z is equal to -5, or 0 is equal to -5. True or false statement? Of course, that's false. So anytime you end up with a false statement like that, there's no solution. You can automatically say, therefore, no solution. And then we can say the system is inconsistent. So basically what that means is you had basically two planes that were parallel to each other. So you have a plane like this. suppose, and then you have another plane that's up here that's parallel, like that, and that's not a very good picture. So, but basically, it's a parallel plane, and they don't intersect at all. So that's what happens when you get a false statement. So false statements are good because then you know it's going to be simple to solve. Okay, let's look at another one and see what we get there. Let's go on now to another case of a system. So this is the type of system that you will have. Let me see where we're at. Okay. It'll be a dependent equation and a consistent system, meaning there's going to be solutions. So we'll talk about what it might look like later. So the first thing you want to do, as usual, is you want to write in standard form. So make sure we do that. Let's put it right here again. Write in standard form. So you can see that this is not in standard form. We want to distribute the 3, bring over the 2x. All right, so try that. Let's go from here to here, see if you can get that. You can take a couple steps to do it. So you want to have it in that descending order. I'll just go ahead and write standard form right here. So ax plus by plus cz equal to d, like that. And that's what we have. So we have this form. Then let's write this into the matrix, writing the coefficient matrix, 3, 11, negative 3, 1, 1, negative 1, 1, 3, negative 1, and the constants. Okay, so from there, go ahead and row reduce. And that's what this left-hand side is over here. So row reduce, getting zeros in this lower left-hand corner. So pause the video and take a moment to do that. And when I erase, it'll erase everything, but that's okay. We'll talk through it. Okay, so just look at the left-hand side for now, coming down to here. So you should get, at some point, one whole row to zero out. So the last row should zero out completely. So what that means, remember it's x, y, z, that means 0z equals 0, like this. So 0 times anything is 0. We know that. So that means z can be any value. Z can be any real number in here. So we basically, and it'll still be a true statement. So we let z, now I like to change the variable to t. That's the standard practice of what to do. The book doesn't do that so much. I think they just use z. They just say z is a real number, which is fine, but this is the way most of us do it. So I let z be t, an element of the reals. Remember, that means element of. Now, what you do is the same as before. You back substitute and you let z equal t. So you go back to the previous equation, which says 3 times x plus, let's see, where is it? Well, this is it right here. That just says y is equal to 4. So there is no z for this one. So that's done. Then you go back to this equation and substitute for x and y. So, or not x and y, I'm sorry, for z and y. So y is 4, so it's 11 times 4, and then negative 3 times t, because that's what z is, some arbitrary value. Now solve for x. Right, so you solve for x like this, bring x over, and you get x in terms of t. So then your solution set would look like this. It's still x, y, z. So you still have the set of values, and usually we do it like this. So it's always set x, y, z. Okay, but then you put in what those values are. So there's a couple ways of writing this. This is good enough. You can say what x is. So x is t minus 19. Y is just 4 in this case. And then z is t. Okay, and that's good enough. And usually you say something somewhere for t in the reals, kind of like that. So that's the form we usually use. Okay, let's do another example. A little different in this case still. So what's happening here, basically you're getting the intersection. So what it means then is the intersection between the planes is a line. So the planes, and that's you want to maybe look up. You have different planes that come down. So like just look at the room. Look at each corner of the room. And if you look at just two planes, then you can tell that the intersection is just that one line. But picture another plane coming in, if like you turn your computer or something and it intersected that line, then that's the intersection, is that line. So you have planes coming in and intersecting in different ways to create that line of intersection. So that's what that represents. Okay, let's look at another one. Might come around. Again, I'm just going to set this one up and then you can solve it. I'm not going to go through all the details in the video. So it's 2x minus y minus 5z equal to negative 3. X minus 2y minus 7z equal to negative 12. So this is missing basically a whole equation. So basically you have two planes then. You have two planes like this, and they're either going to be parallel and not intersect, or they'll be tilted a little bit, and the intersection will be a line. So that's what's going to happen in this case. But you set it up the same way. So 2, negative 1, negative 5, negative 3, and then 1, negative 2, negative 7, negative 12, and then you put in your 0, 0, 0, 0, like that. And we still want to reduce this and simplify it to get the right form. So I'll show you that later. Let's see. There's a couple steps that take a little bit of time. So see what you get. See if you can mimic what's above. I will either post this or do a catch up on another video going on to 6.3.